Now they should be in full screen mode. Okay, so I don't know if you remember from yesterday, we were discussing about the CKM matrix elements, and I wanted to explain you one of the elements, how to measure, for instance, one of the elements that it is BCB. Okay, the transition from a big quark to a charm quark. This is a process that it is at the tree level, and it is, but it is in any case changing generation, and it is one of the measurements which has been measured from long time. If you remember, we were saying that at the beginning this CKM matrix element was measured, or was the first result that we got was from Mark II long ago in the 80s. And then at that time, what it was measured, it was the V lifetime using the primary, the impact parameter, and the error that it was get at that time, it was 20%. Okay. Then I was trying to explain that okay, it is the things are not easy in terms of measuring this CKM matrix element, because it is not so clean. What you have, it is all the hadronic effect, all the QCD interaction here. And this has to be, all these effects have to be parameterized in terms of what we call the form factors. Okay, in the case, in this case, these form factors depends on Q squared, which is the form momentum transfer between the initial state, the initial hadron, and the final hadron, or just the form momentum sum of the lepton neutrino system, and the configuration. So it comes from the minimum Q squared, where you have the maximum momentum transfer, or the maximum Q squared, where you have the maximum momentum transfer for the lepton and the neutrino. Okay, and then you have the star mesonin at rest. And so then the differential decay width, the number of events that you are expecting for a specific channel, depends on Q squared, on this variable, and you can measure this number of events as function of this variable, and then it will give, or it has dependence of the Fermi constant that you know, the VCB matrix element that you can extract, one kinematical function that you know, and these form factors which have to be calculated by QCD methods like lattice QCD calculations. Okay. And the channel that I'm going to, you can use different channels, different exclusive channels, or you can do it also in an inclusive way. The one that I'm going to explain, it is the B meson going to a D star. The D star, it is a compound state from a C and a D bar quark, which decays into D0. So I am going to show you here. Okay, D0 pi, sorry. So this is one measure that it was performed 20 years after Mark II, and before the B factories were starting, and it was at LEP, at CERN, in the Delphi experiment. It was from set decays. I don't know if you remember yesterday, there were different processes to obtain B hadrons. One, it is the epsilon 4s energy, like Belle II, that you know well, or Babar or Bell experiment. The other is from proton-proton collision, as LHC that we will be talking today a lot, or the other, another way, it is from set decays that they were produced at the LEP experiments at CERN. Okay, in the case of the set, because the set it is more has more energy, what happened it is that the B hadrons, as compared to, for instance, the V factories, which have just 1 GeV of momentum, the V hadrons here in those experiments, they were much more boosted. So the energy, I think it was about 30 GeV. And then the separation that you have for the V, because then it was flying more, it was about 3 millimeters as compared to what you have seen for V factories, that it is order of 200 microns. So then the separation was able to do it very well. The problem is that, of course, you didn't have so much statistics as compared the B factories. But this was a method to measure. So then you can see you have a primary vertex. So you have the set decay, and then you have a primary vertex. You have a production of a set, and then decays, and then you have a big quark, and which hadronize, and it decays, and it decays to a D0, and then a lepton and a neutrino. So this is the process, and the D star decays to a D0 and a pion. Okay, and the D0 you can also reconstruct it because the D0 also decay into a kaon and a pion here. And then if you reconstruct the mass of the D0 pi, what you have it is the D star mass, and then you can do the mass difference between the D star and the D0, which corresponds to this pion, okay, which is very soft usually. So then you have a very, very clear peak, which is giving you, which is your signal, okay? And from this signal, you can extract, you can measure the Q square distribution, and it will be of this type, for instance. Okay, so you can see this was in the Delphi experiment. You can you see the different the different background contributions, and okay, there was not too much statistics, but still it was possible to measure. At the end, what you do if because you have to extract this VCV matrix element, you have to do it at a point of Q square, which is a maximum Q square, because you know the form factor normalization at that point. Okay, so at the end, what you do it is to extract the VCV matrix element from this point. So then you have to measure very precisely. So at that time, the error, so the VCV error was about 5%. Then they came the B factories, the fantastic B factories, Belle and Babar, which as compared to LEP experiments, the products of the B hadron decays, they are very, very clean, and then you can distinguish between all the different drugs. They are very, very good detectors, and they were specifically designed for doing this kind of physics, the Flavour physics. So I think Karim also will tell you a lot about how to reconstruct events, or if you are working in Belle, I think you will not very well. Just something that for you to know it is that there is a way that so in the Belle and Babar experiments, so you are forming a B0 and a B0 bar, which are just neutral, and your signal, it is coming in this, it will be a lepton, a neutrino, and any other thing, or if you have exclusive, it will be a D star or a D, or if you have inclusive, you will have everything here with CHAM. And what one can do it is that, okay, this is going to be my signal, but I can also reconstruct all the other process coming from the other B. So all the other products. And this is what we call hadronic tags in the case that we are reconstructing an hadronic mode from the other B0, not our signal, not the one that we are interested, but the other. Or in the case that you have a lepton in the other side, in the other B decaying, then we call it a semi-leptonic tag. Okay, and then one can reconstruct that, and then after that we can reconstruct our signal, and then we know we have a lot of information about the event from the other B decay. Or we can just do it in an Anantha way, which is just we don't care about what it is happening with the other B. We are just taking into account what it is our signal. The advantage of having a hadronic or a semi-leptonic tag is that you have high purity because you are reconstructing everything that it is happening here almost. And the penalty is that you have less number of data because you have to reconstruct everything, so you are losing by efficiencies. The untag method, what it has is that you have much more statistics as compared, but you are not so clean as in the case on this case. I think Karim will tell you more about it, but just for you to say. So then you can do the measurement of these CKM matrix elements. You can do it by using hadronic or semi-leptonic tag, or you can use it untag. So there are many methods, and then there are many measurements at the B factories. Okay. Usually what it is done, instead of Q squared, you can also express the differential decay width. You can express this in terms of what we call the W, which is just the product of the four velocities. So it is just related by Q squared. And this variable runs from 1 to 1.5. So now, instead of the form factors, these form factors are depending on this variable, and they are normalized now. Instead of to the maximum, it is to the minimum of W, okay, because they are related like that. So this form factor has a normalization and also has a shape depending on Q squared, depending on W. And it is usually, it is normalized by the heavy quark effective theory, which is taken, okay, that you consider that the quark, the heavy quark, it has a very, very large mass, then this will be about 1, okay? Lattice Cassidy calculations they have performed, they have a very precise with time of this matrix element, and this is the value that they are computing at maximum Q squared, which means W equal to 1. Okay. The very good thing is that Belle and FLAVOURS have a lot of data. So Belle, it is about 700 inverse femtogram. So then it is possible not only to do an analysis that you are counting the number of P to D star lepton neutrino decays depending on Q squared or W, these variables, but you can also do an angular analysis of all the process. So then you see that the spin of the different particles here. So then you have the V0 is 0, the D star is 1, and the W, you know, it is 1. So then you have an angular distribution. So if you can see here the different angles, then you have the D star and the W. So then the W decays into a lepton and neutrino, and the D star decays into a D0 a pi. So then you have the definition of the angles, and you can do the analysis. And then with all this data, if you have about 120,000 B2D star lepton neutrino decays, taking into account muons and electrons, and even performing an analysis with typecats, you have very few backgrounds. So you can do a very good analysis, and you can see this is the W corresponding to the Q squared. Then you have the different angles, so the lepton angle and the other angle from the one that it is different from the D, and then from the two planes. Okay, so from that it is possible to do a 4-dimensional fit, and at the end you can determine the form factor shape and also the VCB. Okay, you can see how well the data it is agreeing with the predictions. Okay, after the fit, and you remember that okay, we are extracting the VCB from this zone, okay, which is less populated. So this is the result at present for VCB. You can see this is from this was before from the LEP experiment, which was the error. Now as compared how FLAVOURS and Belle they are performing, and at the end what we get. So here you have this is the normalization of the form factor and the CKM matrix element. Okay, this is some correction that okay, they are there, but the error it is about 1%. Okay, if you compare, you have this is the normalization. So this is the VCB times this normalization factor, and this is the parameter that it is defined the slope of the form factor. So then you have it also into 2D planes. So then you can see how things are agreeing at the end and how results have been improving with time. Okay, and this is just a result for VCB. For VUV that we were discussing yesterday, also it is a similar way to perform. Now in the case of the VUV, it is much more complicated because you have much more background. You have to reduce the charm background, which is much more abundant. But I mean, it is a similar thing. And respect to the question that that I had yesterday, I don't know if who was saying that it was very interesting because we were discussing about the inclusive and exclusive decays, because depending on the final state, you have a description from the theory, and in fact for VUV, for the CKM matrix element VUV, which is more suppressed, the theory, if you are using inclusive, this depends on the energy scale that you are treating, but it is the error is large. Now at present it is even larger as compared to the statistical one, and also from the exclusive. Okay, this was at the B factories, which have a which can reconstruct all the event and have a very good estimation of the neutrino energy and direction and everything. But if we want to do this kind of measurements at LHC B, one will think, okay, this is very, very complicated because we have neutrinos and you have a proton-proton interactions and you don't know exactly which is the energy that it is carried out by the p hadron. So how are you going? And you cannot reconstruct the neutrino because you cannot do you don't have all the kinematic constraints in the event. So at LHC B, at proton-proton colliders, the semi-leptonic decays are really very difficult to reconstruct because you don't have all the information about the event. But even like that, this has been possible to do at LHC B. And what it has been done, it is to measure, for instance, the ratio of two decays when it is the lambda B going to a proton, a muon, and a neutrino, with respect to the lambda B going to a charm baryon, a muon, and neutrino. So this is just the ratio of the CKM matrix elements, VUV and VCV square, and the ratio of the form factors, which can be calculated again by lattice QCD, and now they have about 5% accuracy. How can we measure if we don't know, if we don't have all the information of the neutrino? How can we do it? Okay, the good thing that we have at LHC B, it is that we know very well, we are able, as I told you yesterday, we have a very good impact parameter, and we can determine very well the vertexes of the processes. So what we can do it is to use just the information from the primary vertex and the secondary vertex. So when the lambda B is produced and when it is decaying, and then then from these two vertices we can infer which is the lambda B momentum or direction, let's say, more than momentum, the direction of the lambda B, and then from that, okay, we are able to reconstruct the muon and we are able to reconstruct the proton, so we know the momentum of this system. So then we can infer, knowing the direction of the lambda B and the direction of the vertexes, and knowing the direction of the p mu system from the mu and the proton, then we can infer what it is the direction of the neutrino. Okay, so then from this transverse momentum, we can with this information we can reconstruct our events. Okay, it is difficult, but we can this. So what we do it also it is to select a high Q-square region, which the theory is more precise, and this is the variable that we use, that it is the corrected mass, which is just the mass of the proton mu or hadron mu system, and this transverse quantity, this transverse momentum. Okay, you can see here, this is how it looks like. This is for the case of so for our signal, which is depending on VUV, and our signal that it is depending on, or the normalization, if you want, of VCV. So you have much more events here as compared to the number of events that you have in the V2U transition, and you can see how difficult it is. This is our signal as compared to the big amount that you have from charm, okay, and other decays. Okay, but even like that, it is possible to do it. And this was the result that it was obtained by VCV. And using the word average for the exclusive VCV, from the exclusive VCV that you have seen that it has been very precise, this was the result that it was obtained for the VUV matrix element. What happens, and what it is in fact the present status, and in fact it has been like that for a long time. I think it is for I would say 20 years already, that we have a problem when we compare what it has happened with exclusive and inclusive measurements. It is probably coming from the theoretical description, from the theory, how it is described, the inclusive and the exclusive ways. But now that is QCD calculations are very precise. So the exclusive, the form factors, we believe of them. there are some issues related to how you parameterize these form factors, which depend quite a lot, much more as we were thinking about the parameterization. But even like that, still we have what we observed is there is a big difference when you are computing or when you are measuring VCV and VUV in an inclusive way or an exclusive way. Okay, so here you have these bands. This is VCV and this is VUV, and when you compare, so you can see this is the way that the exclusive measurement of VUV, the inclusive measurement of VUV, and then you have the VCV exclusive and the VCV inclusive. Okay, and then you can see that okay, it is not very well. The result from LHCV it is this one, that it is the ratio of VCV and VUV, and this has triggered some models trying to introduce, for instance, right-handed currents or some new physics, and checking, okay, if I am putting in my model some new physics with right-handed currents, this will be we will be able to describe better. I mean, to have a better agreement between exclusive and inclusive, for instance, and this has been argued of that, but it was disfavoring the new physics models, in fact. Okay, so this is the from the different. So this is the inclusive band if you do it as function of these new right-handed currents, and this will be B2 pi lepton neutrino, and this will be the result from LHCV. Okay, so then there were kind of looking for a point where we can introduce new physics. Okay, but this is something that is still standing and we still don't understand. So if you are working on semi-leptonic decays at 3 level, this will be a very good thing that you can try to understand if you want to do a thesis about it, because I think it is still there. Okay, just give you a final image of the CKM matrix status. So this I have just shown you one of the measurements, but there are, I mean, hundreds and hundreds. And at this point, if you put all these measurements, all the constraints that these measurements are doing in this, you remember this eta and rho plane, which is the way that the CKM matrix elements are parameterized, then what we observe is that everything seems to agree well in the same vertex, which means an upper vertex of the triangle, which just means that we don't have inconsistencies, and we are validating the standard model in the flavor sector. And the precision that we have now, as you have seen, as compared to other, it is really, really high. And also what we have to know it is that the QCD understanding it is very important, because it is producing some of the theoretical uncertainties here. Okay, there are two groups which are doing this kind of feeds, putting all the flavor observables together and checking which are the results from the CKM matrix elements with the global picture. You can check both. And I think Marcela Bon, I think she will be talking also next week probably on this. Okay, just a very few remarks, because in principle, okay, we say that everything is going well. Okay, we don't understand this inclusive and exclusive thing from the VUV and VCV matrix element. It is true that VUV, it is not, it is the element that it is the less well known, because you have it's much more suppressed, and the theory is not so describing so well. There are still a lot of uncertainties, but even like that, the global picture it is quite okay. But what we have observed in the previous year, and it is something that it is very puzzled, and it is people are working quite a lot on this. It is that it has been measured the ratio of the semi-tauonic and semi-muonic branching fraction. So it is just, instead of before I was talking about B to D star lepton neutrino, and the lepton was a muon and an electron, and now I'm talking about the B going to a D star, a tau, and a neutrino. Okay, with respect to other muon. Okay, so in principle, okay, this is 3 level, and in principle you are expecting that you have just a W, but it is possible that you could have also new physics. You could have also a new Higgs, a new Higgs, or you could have a leptoquark. It could be also possible if you have some, if you observe that you have some not standard prediction, let's say not a standard result. So the good thing is that the standard model predictions for this ratio, it is quite precise because okay, the VCB matrix element, it is cancelling in the ratio. Both are B to C decays, and also the form factors partially cancel. Okay, so the results, the calculations of from the standard model, they are very, very precise. And also, they allow to test, apart from being sensitive to charge Higgs or leptoquarks, they allow to test the lepton universality. And I think you will have also lectures this week about it. And this was very intriguing because there was a measurement from Babar on this channel that it was 3 sigma away from the standard model. And I really advise you that you have a look to this paper, this Nature paper, because it is very interesting. And then this 3 sigma was triggering the result, the measurements. And at LHC we have done it using different decay channels. So the taus are very complicated also because you have neutrinos, but in the decay. But even like that, we did it with it has been done with 2 different methods. One, it is using the information from the missing mass that it is remaining, and the muon energy. And okay, you can see here the signal, but it is in red. It is complicated, but you have it there. And also using the information from the position of the pions. In this case, you have 3 pions, and we use some normalization channels, which are different in any of these cases. And you can see here also in red the signal. This is just the 3 pions decaying time, and this is the missing mass square. And with these results, and with new also results with Belle, I have not put it, but just it is to give you an idea of this picture. This is for RD star. It is the ratio that I was talking about, B to D star tau nu respect to the B to D star mu nu. You can have also just a D, and this is RD. This is what it is called RD. And in this plane, you have RD star versus RD. And if you see the different measurements, so this is, you have the standard model, and then you have the Babar result, the Belle result, a new Belle result now, and the LHC bands, which are just measuring RD star. Okay, in the other case, you have the 2 measurements. And we observe that we have an average 3 sigma deviation from the standard model. And okay, people can say, okay, 3 sigma, it is 3 sigma, it is not too much, but I don't know in the previous lecture about the test statistics, you know, but if you realize about this, if you put all the measurements together here, what you can observe is that, okay, this is the standard model prediction, okay, and these are the different measurements, and all of the measurements are in the right side. So if I will expect that if you don't have a systematic problem, it is just a question of a statistic, I will be expecting that you have it in both directions. And what we observe is that just in one of the sides. So okay, this is something that it is intriguing. People are working on that, and I'm sure Belle too. So if you are a experimentalist, also I think it is a very good field of research if you are working in Belle too to measure this kind of decays. Okay, and I think this is all from what I wanted to talk about the CKM matrix elements. And so if you have any question, I think it is a very good moment to do it. And if you are there, at least it will be very good to know it. Are you still there? Hello?
Yeah, we can hear you.
Okay. So I see some.
There's one, Arantza, there's one question in the chat box.
Okay. What it is called, you explain in case of tag and untag events, the difference versus high purity and high efficiency. Is tag 1 better over the untag as regards the VCB determination? It is, this is a very good question. So let's go. So the high purity and the high efficiency, yeah, does mean that means the amount of signal and the amount of background that you have. I don't know exactly, but maybe we can have a look here. I don't remember what it is. Okay, it is not there. It is not there. The difference. I will have to check which is the difference in uncertainties as compared for the untag or untag or tag. But I think at present, because the statistic it is too high, I think they have to be quite similar. In fact, in both cases, probably the systematic uncertainties are a bit, for instance, for the background subtraction are higher here, and maybe they are affected. But I think in any of the two cases, or in any of the three cases, I think it has to be the final uncertainty. It has to be similar. If I am not wrong, I will guess that, but I have to check it. I don't know if some of you know it, or maybe Namit, you know better.
No, I don't remember. I think it's eventually it was a tagged one which was better probably with the Bell hadronic tag, but I don't remember the answer.
Hi, this is Shirin. So can you explain how is high purity and high efficiency defined in general?
Of course, so the difference in high purity, what I mean, so you have two things in all the experimental analysis that you are performing. You have your signal and you have your background. So the important thing is to have as much as signal as possible and as much as less background as possible, right? That's clear. And the thing is that if you are reconstructing in this hadronic or semi-leptonic tag, what you are doing it is that you have to reconstruct specific channels, exclusively specific channels. So I have to check this B decay into this mode, going to a 3 pions and a count, for instance. Okay, so then this has an efficiency which is small. It is a few percent. It's a branching ratio which is it's small. So then the events that they are decaying here, they are going to be less events as compared to all the total branching ratio, right? So that means that the number of signals that I'm going to use, that I'm going to have available if I'm using this hadronic tag, or in the case that I am using a leptonic tag, because then you have the branch in here, you have just a proportion of the events that they are decaying into a semi-leptonic decay mode. Then the statistic that you have here, the number of events that you have here for your signal, it is going to be less as compared to the case of the untag. Okay, that's clear?
Yes.
Okay, and but the thing is that because you are reconstructing all these events, all these decay modes, also you don't have other particles that they are there that you are thinking that it is your signal. Here you see you have 1, 2, 3, 4. You will have 5, or okay, depending on this, but okay, you will have some number of particles and the lepton that you know everything apart from the neutrino. So then you reconstruct all, and then you can see very well which is your signal, and you have a very, very few background. But here, for instance, in the case of the untag, what it is happening is that, okay, I'm thinking that this, for instance, if I have a pion, okay, I'm thinking that this pion is coming from my signal, or my D0, let's say. My D0 is coming from my signal, but maybe it is not coming from here, maybe it is there. Maybe it was coming from the other B, because I don't know exactly what it has happened with the other B. Then that means that I can exchange particles, for instance, and then I will have more background here. Okay, so I will have more signal, but which means that I will have high efficiency, but I will have also more background. Okay, and in this case, I will have less signal, so the efficiency is less, but I will have much more purity, that I will have less background. Clear?
Yes, thank you.
Okay, you're welcome.
There's another question. Is there any other inclusive versus exclusive mismatch other than VCB and VUB?
No, I don't think so. I think in the charm, for the charm matrix elements, I don't think so. No, I think it is just in the case of at least so big as compared. But this has been for long ago. So it is still something that we don't understand.
There's one more. From experimental point of view, is there any advantage of detecting muons in the final state as compared to electrons?
Very good question. Can you reply it? Who was this? Who was given this?
Ipsita?
This,
Can you try?
who?
Ipsita. Ipsita Ray.
Ipsita. Can you try? What would you say? What it is depending on what? You think, or anyone, maybe if someone can figure it out, but it will depend. It is an advantage, or this depends on what? It will depend on what we have as a detector, right? So if we have a very good muon chambers, we will be very efficient, and we will be doing very good precision on muons. If we have a very good electromagnetic calorimeter, then we will be much better doing electrons. So this depends a lot about the experiment. So for instance, in the LHC B, we are much better in muons. Our muon chambers are much better are much precise as compared to the calorimeter. But I think in Belle II, the electromagnetic calorimeter, it is performing super good. So it is very good for electrons, right? So at the end, this depends on the physics that you are expecting. It is about the same, but depending in muons or electrons, this depends on just on your experimental apparatus.
Yeah, hello.
Yes.
Yeah, sorry, I got disconnected. Can you please repeat the answer?
Which one? For electrons and muons?
Yeah.
Yeah. So I was saying that if from the experimental point of view, this is just a question of how it is your detector. If you are very good at detecting muons, if you have a very good muon chambers, then you will be able to do very good physics with muons. If you have a very good electromagnetic calorimeter, you will be able to do a very good physics with electrons. And I was just comparing, for instance, in LHC B, the muon chambers are very good and very precise. We have a very good identification of muons. So then the result with muons are always better than with electrons. And in the case, they are more difficult to reconstruct. And in the case of Belle, I think the electrons are better as compared to the muons. So this depends on the experiment, really, on the detectors. Yes, exactly.
Yeah, okay.
Yeah, exactly.
Okay.
Misra. Yeah, exactly. Very good play. That's good. You have to figure out. It's always good to think about it. Okay. So I think if there are no more questions, we can move forward.
Hello.
Yes.
Can you little bit explain about the use of corrected mass you have just shown in the B2D slide?
I didn't understand well. Can you?
So you have used
in the BUV, in the LHCb, you mean?
Yeah, here's a corrected mass. So use a corrected mass in the experiment.
Yes, exactly. So the corrected mass is just has this definition. So which is just you have understood what I have explained for this transverse momentum?
Yes.
Okay, so then you have this quantity, and it is just that you have the mass of this h mu just means the proton and the muon in the case, or the lambda c and the muon. Okay, this h means just the hadron that you have. So what you have it is that you do the form momentum, so the invariant form momentum of these two systems, of these two tracks, and you add this the quantity. Okay, it is like to have the complete reconstructed momentum. Okay, this will be corresponding to the lambda b to protons in this. So it will be the lambda b mass corrected by this quantity, by the neutrino. It is like it is giving the correction of the missing neutrino because you are not able to infer it from other quantities.
Okay, got it.
It's okay.
Yeah.
You got it.
Yeah.
Okay,
Yeah.
very good. It's okay. Any other question? Okay, if not, I think we should move, and I'm going to change lectures. So you have the link in the other. And now we are going to talk a bit. We will not have too much time, but it is not a problem. We will continue tomorrow. So I mean, I want that you understand even if it is less than when I was expected, but at least that you understand. And if you have questions, please don't hesitate to ask, because I think the important thing is that you get something, even if it is not too much. Okay. So now I'm going to talk about rare decays of heavy hadrons, which is a very, very interesting subject if you have heard about it, because it's where we are finding a lot of anomalies, and they are like also giving some hints of there is something happening in the flavor physics sector. Okay, and this is it is quite intriguing. You will see it. Okay. So first of all, what is a rare decay? Okay, so it is like, you know, it is four-leaf clover. I don't know if you are familiar there with in India, but this is very, very strange. Usually they have just 3 teeth, and in Europe it is a symbol of good luck. So if you are able to find one of these clover, that means that you are going to have, you are going to be lucky. So what it is really a rare decay, something so rare as it is. So this is 1/10,000. So what we are talking about rare decays, it is things which are very, very, the branching ratios are very small. And in particular, what we are talking, it is the transitions. We have been talking before on the B to charm or B to U transition, which are at the level, which was the emission of the W going a lepton and neutrino. Now what we are going to have, it is a B2S or B2D transitions, which are flavor changing neutral currents. And as we were seeing in the gym mechanisms, this can only occur through loops. Okay, you have different diagrams. You have penguin and the box diamond, the Feynman diagrams. So you will have things like this type. Okay, to be able to have this transition in the final state. And because they are going, so they have to be produced in this way through these loops. Then you can. It is possible that you get that there are new particles there in the loop giving some signals. Okay, so they are a real good proof for physics beyond the standard model. And the types of rare decays that we have, they are three. The leptonic decays, where you have 2 leptons in the final state. It can be 2 muons, 2 electrons, or 2 taus, just 2 leptons. You have a transition here going for B2S. You can have semi-leptonic decays. In this case, it is semi-leptonics, but not at 3 levels. So you have to distinguish there. This is rare semi-leptonic decay, so flavor changing neutral current. And so then you have S or D here. And then you have 2 leptons and a quark, S or D, that it is going to hadronize in another particle. So in the difference is that in this case you have 2 leptons. In this case you will have 2 leptons plus an hadron. Okay, this is semi-leptonic. And the other possibility is that you have a radiative event where you have a B quark, which is transforming a S quark or a D quark, and then you have an emission of a real photon. Okay, so the difference in the branching ratios runs from 10 to the minus 5 in the case of the radiative, 10 to the minus 7 in the case of the semi-leptonic, or 10 to the minus 9 in the case of the leptonic. So it is really, really very, very rare processes, which are very difficult to distinguish, to reconstruct, no? Because it is very small. The good thing is, from the experimental point, is that, okay, you have leptons and photons, and this is always, leptons and photons are always good if you have a good electromagnetic calorimeter, or if you have a good muon chambers, because you can reconstruct it for high momentum leptons or photons. You have a very clear signature. Okay, theoretically, the good thing is that there are some of the observables which are very clean, and they can be calculated in terms of the Wilson coefficients, and I'm going to talk very soon about that. Okay. So what do we need? What do you think that we need if we want to reconstruct, to be able to see a rare decays of this kind? Of course, because the branching ratios are so small, we need a lot of data. That means that we need high luminosity and large peak cross section. You remember the equation from the number of events, that it depends on the cross section and the luminosity. So for that we have the LHC experiments now, and we have also Belle II. So these experiments are very good for measuring rare decays. Before it was not possible because the experiments had not so much luminosity, so it was much more complicated as compared to now. Okay, and what we need also, we have to have a good high momentum and good impact parameter resolutions, because you have a signal, and this signal you have to separate it from the background, because you have much more other different decay channels which are going also for instance to leptons or to photons or to other decays that they are going to be much more abundant as compared to your rare decay. So you have to be very careful and not to misidentify some of the backgrounds of your signal. Okay, so you remember that this the definition of the impact parameter, that it was just for instance in the case that you have a muon, so the muon can come just from the primary vertex, so not from the decay that you are looking for, not from, for instance, if you are looking for a BS decay going to muons, maybe if I have just that they are coming directly from something produced here, then I will misidentify it. But if I measure very, very precise the impact parameters, this will give me that this muon, it is coming not from the original point, but I mean it is decaying from a BS decay, and then I will be able to distinguish from there. I mean, a muon coming from there or a muon coming from here. Okay, so this is very important to have a good impact parameter resolution. And also the momentum resolution, it is very important, because if I have a good momentum resolution, because what I'm doing is compute the sum of for momentum for getting the mass peaks, the invariant mass distribution. So if as much as resolution as I have in the momentum, as much as resolution I will have in the mass, okay, in the mass distribution. So this is, you have the comparison for the momentum, the resolution of the momentum for LHC B, Atlas, and CMS, and also for Belle II. So this depends, the resolution of the momentum depends on the momentum. So if it is depending on the range that you are for your tracks, and usually you have, this is the momentum distribution. So the maximum tracks that you have, it is around here, and then you have depending on this momentum, you have different resolutions. So it runs, for instance, from 0.4 to 0.6% at LHCb, because you remember that we were defocusing the beam, so then it is much more precise as compared to Atlas or CMS. And at Belle II, of course, also it is very precise, the energy is less, and you are able to reconstruct it very good. Okay, this is for the momentum resolution, and here you can see this is for the impact resolution also, if you compare LHCb and Atlas and okay, Alice, this is just to see what it is. And you can see that the momentum, depending on the momentum, okay, for instance, in this range of here, the resolution, the impact parameter resolution, it is very good. Okay, it is a few microns, tens of microns. Then that means that we can reconstruct our signals. For instance, in the case that you have I mean, you reconstruct the mass of two muons. If we evaluate which is the resolution, in this case, it is evaluated for the upside to decay into two muons for LHCb, Atlas, and CMS. But taking into account the momentum resolution that we have, the momentum resolution in these different experiments is about 13 MeV for LHCb if you reconstruct all the event of your signals, for instance, in the 2 muon case, or it is much higher for Atlas and CMS. And for Belle II, it is really very good, okay, because the momentum resolution is very good. And why it is important to have this good mass resolution? You can see it very well here. Okay, this is the mass of the 2 muons. If we are looking for a very rare decay of 2 muons, then you will see that you have something like that. If my mass resolution it is very big, this can be fitted to anything. So suppose, okay, I'm trying to distinguish here a peak. So if I don't have a very good mass resolution, I cannot distinguish between different peaks. In the case that my mass resolution, it is good. I can, for instance, distinguish between things which have masses very similar, like it is, for instance, the case of the BS and the B meson. Okay, so then I can, if my resolution is good, I will be able to separate. If my resolution it is not good, I will not be able to do this kind of measurements. Okay, so this is why it is clear. How do we measure branching fractions? This is a very important thing. This is, you have seen the PDG and it is full of measurements of branching fractions. Some of them maybe just one branching fraction, it is, or branching ratio, it is just a PhD thesis. So it is 4 or more years of work. So it is not something that it is trivial. So it is really important. It is really an important thing that it is telling us many things, and it can be a sign of new physics. How do we measure these branching fractions? Okay, this depends on the environment, the experimental environment that you are. So in the case that you are, for instance, at the ε4s energy, and then you have to be measured at the final state, you can measure absolute branching fractions. That is that, okay, I can reconstruct precisely all the events because I have a very good and hermetic detector. Let's say Belle II, Babar, or Belle. So I have a very good detector and I can reconstruct everything inside what it has been happening, okay, in my process. I have one of them which can decay in these particles, and I reconstruct the form momentum of each of these particles, and the other, it is, for instance, my signal. This will be a electronic decay where I have a tau and a neutrino in this final state. I'm interested in this decay. And but I can reconstruct everything. Okay, so to measure these absolute branching fractions, we need to know precisely how many events are produced and reconstructed in my detector. For that, I have to understand very well how it is my detector, which is the efficiency of my detector. My detector is able to reconstruct, or I'm losing. I have holes in my detector, and I'm losing some events. I have to understand very well what it is the response of my detectors in terms of the reconstruction efficiency, which is usually taken from the simulation. We have, in all these experiments, we have good simulations of our detectors to understand well, and usually we try also to validate it with data. So, for instance, in this case, the number of this signal that I want to detect, it will be just 2 times the number of the ε4s that I have, by times the branching ratio that it is, so the number of BB events that I am having, by the branching ratio of the B going to tau nu, that it is the observable that I want to measure, times the branching ratio of the tau going to my specific decay channel. That is, I can take directly, for instance, from the PDG or from the H-Flavour, so the heavy flavor averaging group, times the efficiency of the reconstruction efficiency that I can take it from simulation. So the number of events that I'm getting, has this formula, and from that I can get the value of the branching ratio, that it is the thing that I want to measure at the end. Okay. And here, the good thing of the absolute branching fraction, it is that because I know the other event, because I know this event here, and I have a similar information of the branching ratios and the efficiencies in this part of the event, I can know very well which is the number of BBNs that I have. So at the end, I will have a very good measurement and absolute value of the branching ratio of the beta 1. Okay, in this case. But if I don't have all the information about all the event, and I don't know exactly what it is the particles that they have been produced, what I can do it is to measure relative branching fractions. And this is, for instance, what it is done in proton-proton collisions. What we need it is to have, so we are measuring some decay channel. We are interested in measuring some decay channel. For instance, in the case, we are interested in measure the branching ratio of the B, another rare decay, to the BS to phi gamma decay channel. And then what I need it is I need to refer this to use another decay channel, which I think that it is very abundant. So I have a lot of statistics. So it is not going to introduce error in my measurements because I have a lot of data from my normalization channel. And that it is also very well known. I mean, that I know the branch ratio. So for instance, in this case, the B2 castar gamma, it is more better known as compared to the BS25 gamma decay channel. So then I'm going to, if I want to measure the BS25 gamma, I will refer it to the B2 cluster gamma. What do I have? In this case, I will have the first, it is this ratio of fragmentation function. This is just giving the probability of a B quark to hadronize in a BS meson, or a D quark to hadronize in a D0 meson. Okay, so this is coming from there. And then I will have the branching ratio of the BS25 gamma or the B2 cluster gamma. Then each of the individual particles in this decay, the phi of the K star, they will decay in some specific channel that it is good for me to reconstruct. For instance, in this case, 2 counts, and in this case, 2 pions. Okay, so this will be the kind of particles that I will have. And then I will have to multiply by the efficiencies of my detector. Okay, and what we usually try always when doing relative branching fractions, it is to use channels which are similar, so then some of the efficiencies they can cancel. Okay, because you have, for instance, at the end you are detecting, in both cases I'm detecting a photon, in both cases I'm detecting 1 count. Okay, so then this will mean that you will have cancellations of efficiencies. And also, if we use the same data, so here you are missing the factor of the luminosity and the cross section. If you are using the same amount of data, I mean the same data sample, these factors will cancel. Okay, and the efficiencies of my detector usually have different contributions, and as I told you, some of they cancel in the ratio, so that means that at the end I'm going to be less sensitive to the systematic uncertainties coming from the knowledge of my detector. So for instance, you have in this efficiency of the selection, you have the detector geometry. So the detector geometry, it is just, in the case, for instance, of LHC, I told you it is just covering a 30% of the solid angle. So this is cancelling from in the 2 cases. The trigger, it is a very, very important thing, because it is what it is giving you that you are recording an event because you have a signature of some important or some interested event. So then this is quite common. Usually this it is giving the selection of your event, and it is quite common, and it can be also be canceled. You have the reconstruction of your event, how you are able to reconstruct in the different detectors. So for instance, in the case of the photon, you will have the same. And then you have some specific, you have to do some specific work to better subtract the background. You use usually multivariate techniques, machine learning, you can use BDTs, you can use whatever to subtract your background. So then you have to check which is this ratio also. And the particle identification, so if you have different, in this case, for instance, for the photon will be the same, or the tracking, if you have tracking particle identification, if you have similar or different tracks, okay? And then each of these ones, so it is a complicated thing. You have to understand very well all of these efficiencies to be able to compute at the end the branching ratio that we want to measure. Okay, and this is important. We have to measure very, very precise, because at the end you are going to compare with the standard model, and if you are having the same, I mean, if you are compatible with the standard model, that means that okay, everything is agreeing. We have a super good standard model, as Grossman is saying. Or if we have a problem, we have a difference in the branching ratio that we are measuring as compared to what it is calculated in the standard model, then we will have some sign of that something it is happening there, and we have to investigate. And I think, I don't know what it is the time. Oh, I didn't know that we were so late. I'm sorry. Sorry.
Yeah.
Okay.
No, it's okay. It's okay. It's okay. It's okay.
I'm sorry.
Professor Grossman is here, so
yeah,
we can,
I think it is. Yeah, I think we can stop here. I'm sorry.
Yes, this is a good place to stop. So, if there are any quick questions for Arantza at this point, please go ahead. Otherwise, we'll have
I think if
last
not,
lecture tomorrow, and please feel free to interact.
Okay. So thanks a lot, and see you tomorrow.
Yes, thanks. See you tomorrow, Arantza.